But I don't think I often talk about in this room which is astrophysical dynamo theory. Um, so, but it is also a demonstration of a code, which so this is done with collaboration with, of course, some people, me and some other senior people here, but also this is already working on this code has already started in Finland from a PSC. So basically, Astaroth as a code has been in a development for a while. So far, most of the publications we have are essentially computer science. In a sense, it's actually very efficient of what it's doing. There's a very well justification that development of it has taken its time. But I then took that, okay, now we have the code functioning, things are there, so let's use it for science. And I've been working on some other things with Astaroth too, which are work in progress, but this was then that, okay, we need something that is pretty straightforward, in a sense, to test with Astaroth, where we have also existent earlier results where we can compare what we get. So we went to what was familiar to me and my old group back in Finland, was a turbulent dynamo theory. So, okay, first a little bit about the code. So, Astaroth, it's been developed essentially started from Finland and later me here, but it's mostly been developed by two people. Me and then a computer scientist Johannes Pekkilä in Finland, and then some other people here and there. But basically, Astaroth is a code where you can accelerate GPU computing. You can accelerate numerical computing with GPUs. And as it's now, because we have the computer scientists working on this, that it's actually now in the form of API or application programming interface, meaning that although in principle now the support what I've been having is resistive MHD with high order finite difference method. You know, if you need like stencil-like operations, basically where you need to compute neighboring numbers, then compute them together to get there's a numerical result. Could be even completely some like game of life image analysis, image processing, even whatever. But my main driver has been the MHD, and it's pretty generalizable API form, API engine type of engine. So perhaps even in the future we might have even Python interface, not yet, but I've been joking about it. It might even happen. So specialty about this that it's very efficient for high order operations with stencils. So like you have, because high order stencils, they are not trivial to optimize on GPUs. For example, there is like what was for example the recently popular GPU code, which like Miikka I'm using this. Sorry, I forgot the name. Anyway, there are some existing GPU codes. Fargo, yes. So there are some existing GPU codes which also do finite difference, but the thing is that they are of lower order finite difference, where GPU optimizations of those things are much easier. When you go to high order, you come to issues with memory latencies, and you need to do some hard work to deal with that. So, after the inspiration has been in these like vertex processing pipelines, which come from like graphics processing even for like computer games and stuff like this. So you can actually make it used efficiently for this sort of computation. Also, there is a kind of internal programming language, Astaroth, which you can use to describe what sort of stencil operations you want to perform. so that you have a sort of a C-like instructions you can give it to that. And then basically the optimization stuff happens under the hood, that as long as you can be able to formulate your problem in terms of this domain-specific language, you can just write it, and then the optimizations, it happens within the engine. And we have also multi-GPU support. This work I've seen done with single-node multi-GPU, but also pretty soon we will merge the MPI like multi-node GPU things to the master branch. So compared to a CPU node, not a single CPU node, we get more than 30 times speed up from this. Okay, so much time explaining one slide, but I try to still have 10 minutes with the science. So what is this small and large scale dynamo? So dynamo in general is how do you generate like magnetic fields in many of the astrophysical systems based on turbulence. And there are two basic principal types of dynamo. There is the small scale dynamo and there is the large scale dynamo. And we are looking both here at the same time. So in small scale dynamo, basically you have a turbulence. It doesn't it can be just even compressive turbulence, just turbulence. And then you can, if it's MSD and you have sufficiently low resistivities, then or higher Reynolds numbers, you can get you start to generate like in smaller scales than the turbulence driving, you can generate magnetic field. There is, for example, this animation over there is in my Astaroth simulation, which is sort of done in this semi-isotropic periodic drive domain. Here is basically magnetic field generated by a small scale dynamo phenomenon happening. And a typical example of astrophysical, like what I'm modeling is very physical process oriented, but it connects to astrophysical context very strongly. For example, both in different places, but for example, one thing about the small scale dynamo that would be like stuff that is happening here on the sun, all the turbulent chaos, there will be some level of small scale dynamo there. That's one example of that. But also can happen in the stellar medium too. I'm just trying to give some example. And then we have the other thing is the large scale dynamo, which is a bit more wackier of these two. So actually you get this chaotic self-organization phenomena, which comes from that you have where you have helical types of turbulence with a twist, and that helicity conservation transfers move energy to larger scales. So you have this phenomenon here where you start like small scale turbulence, and then you can see this anamagnetic field in one direction. So you can see this you can see this single wave emerging here, and this is large in this sort of dynamo, this sort of large scale dynamo wave emerging from chaotic nonlinear process. So these are the phenomena basically now examining. And example of this in astrophysical context is, for example, in my old group we have done like supernova turbulence modeling trying to understand galactic dynamo, which is essentially this sort of a large scale dynamo phenomenon. Yes.
So do you assume ideal MHD in this case?
You always for this we have explicitly resistive MSG, and actually you need for dynamo you need some level of real resistivity. This is now not, and even shouldn't be ideal MSG simulations. Actually, if somebody is doing ideal MSG simulations in focus on dynamo theory, I find it slightly suspicious because then they are not explicit about their Reynolds numbers, because any numerical code will not be perfectly ideal. So, still trying to 5 minutes. Still trying to explain the process a little bit of a flowchart. So the model, you start with weak C field, basically just random Gaussian fluctuations, and then I have the resistive isothermal energy equations, and which is then driven by this sort of a forcing function where you can determine if it's driving like a non-helical sort of compressive turbulence or is it driving like vertical solenoidal helical turbulence. So we have these two prime modes which we use, helical and non-helical, and then what we get, what emerges is, if you are non-helical, it's basically actually you get the small scale magnetic amplification, you get this growing of a small scale dynamo, and in principle in helical dynamo driven dynamo you get the large scale dynamo, but this is where the complication is, because as I argue with our results that small scale dynamo seems to be very often played sport with small scale dynamo. And these result in both in stronger magnetic fields but in different sort of features. So what we did was having this semi-isotropic periodic domain model. This is very standard stuff that's done elsewhere, also developed by Astaroth co-founders. And then, but run it systematically in very many different values for the resistivity, and also running multiple resolutions for every single one. So benefits of the GPU computing is so here is a 3D example of what is happening. First you have more chaotic, then you get more self-organization. This is not a large scale dynamo guided model.
So
Yes.
do you also have a magnetic reconnection in the field line here?
In principle, reconnection is always part of the dynamo process.
But do you assuming some kind of model to do this?
No, this is direct numerical simulation. That's the point. No subgrid models. We are limited by resolution and so limited by Reynolds number with Reynolds numbers within the numerical stability.
Yeah.
So one point of this sort of high order modeling is that this is really, we don't have much subgrid assumptions here. We just are of course limited by some range of Reynolds numbers. And this is the largest current from here example of the lowest resistivities, where it gets a bit more chaotic. Here you have. Okay, so little time. Basically, one focus, we are looking at the growth of the dynamo. So in here, these are the magnetic field Rubin square average curves. So one thing that we are measuring from this is the growth rate, and compare these growth rates together. So there, is there a right laser? So we have now separate pictures for large scale and small scale dynamos. Large scale dynamo is, there are different details, but it's kind of a similar level of the growth rate with some variations. One interesting thing is that the small scale and large scale dynamo growth rates sort of connect at the high Reynolds number or low resistivity edge within a parameter space. So here is, so just to say that we have multiple resolutions, many points, both sides. This is one of the earlier data, so they have like 3 points, 4 points. So this is some nice thing about the GPU. We can just run many of these. Mostly I'm just trying to have a mercy on the data file system in the cluster. That's one kind of limiting factor here. Otherwise, I could generate even more terabytes. What I have. So, trying to understand this more. And now time is almost up. So we see similarities in the growth phenomena, like in the power spectra here. Also, if you look at magnetic field distribution, there is this phenomena that seems that at the high Reynolds edge we have similar kind of growth phenomena happening, so that actually even large scale dynamo the growth is like a small scale dynamo, but more enhanced. And then there is some alpha effect mean-fit dynamo estimates which are, unless you are mean-fit theory people, probably doesn't say much, except we can, with these mean-fit theory estimates, sort of agree with the direct measurements, but when the small scale dynamo really gets to whole, there's divergence in here. So just, I'm sorry, I'm very fast. I explained too much about the code than the science, but now it's time for questions. You can just ask about the science of the code. And actually, Astaroth is a new open source project, so if anybody's interested, you can contact me. And also, the code is available over there. So thank you, and question time.
Any questions?
Realistically, so if you, for example, if I want to apply your code or theory to ISM or something,
Yes.
maybe there could be some. So how's resolution problem? So maybe you.
Well, there is always a resolution problem, but.
For example, if we consider some region, maybe you need to reach some minimum scale that we want to resolve.
Yes.
Then maybe if you consider the limitation of the computing power, we can have some region or in the ISM that we can simulate. So I'm wondering how large which scale we can simulate in the ISM. Maybe on galactic scale it's maybe possible.
I mean, okay, of course there's a limitation of this, that this is not an artificial finite code. So this has been done for fixed grid simulations. So you have to then take that into consideration. You can there is like certain range of values you can go with that, and it's really then dependent on how you think about the problem. I mean, resolution problem is always there. You can't get rid of it. It's just what is the tactic.
What's the maximum simulation scale you can do on GPU?
Speaking of resolution, okay, there are a few different answers to this. One is that for this stage, I work with a single node. I was using the tier GPUs. I use a single node for there. If I want to have this full MSG setup with isothermal full MSG setup, there comes the memory limit of GPUs that for 4 P100 GPUs, the maximum resolution, if I want, with the double precision, maximum resolution is what I could have was 512 cubed. I mean, in discretized, like ×2, so from 2024 cubed, so forth. 2024 cubed you could do with 2 nodes, and then, but now there is also the computer science part of the people they are working on the MPI, large scale MPI stuff, so there we can have easily like, I think they have tried like 4,000 something cubed, for example. This is going massively parallel growth. I just haven't been able to test it here.
Because I was wondering at the end of your result, this dynamo should be very sensitive to the resolution you have in your simulation.
This is why we run this in multiple resolutions.
Well, I don't think it's possible to reach to the inertial scale turbulence. I mean, you need to, because you will get if it's a pure hydro model, you have a commutable spectrums.
We have an explicit Reynolds numbers. Yeah, we are looking at things.
But then for the MHD model, the behavior is still a power over the. You need to reach a very small scale to actually resolve the dynamo eventually, because.
Where do you get this?
Yeah, because if you're assuming, because you want the dynamo, you need to twist, you need to stretch the B field, and you twist. And you need to get the reconnection occurs at the twist. So the dynamo
These things are perfectly tested with this type of models for a long time.
These
many
are from
models.
Alex Zanzari, and at Eason.
I'm not doing anything exotic here. These type of dynamo models have been done for 20 years now. So I don't really understand what you're after.
Yeah.
So it's time, so let's discuss after this session. So let's start all the, so this first session again.